Evening and good afternoon, everybody, to the each and where you are right now. So today I will be going to review like CO2 electroreduction to long chain hydrocarbons on cobalt-based catalyst. So this is the paper that is recently published in Advanced Energy Materials. So let's first go through like a bit of introduction. So we all know like CO2 is the main culprit for the global warming. So we need to reduce the global warming as much as possible. So there is one way like to convert CO2 to produce like long chain hydrocarbons, which we can utilize for the fuel purposes and as a chemicals in the form of oxygenates and these sort of things. So in the electroreduction, we have some parameters that are like very important for the process, like Faraday efficiency, which is somewhat like the selectivity of the different products, and current density, catalyst stability. Like if we want to upgrade to the industrial process, so we want to have some catalyst that is that is going to have like good stability, so that we can operate it for long times. And one last parameter is like a chain growth probability, which is like the production of long chain hydrocarbons. So this is the probability, like how much is the probability for the chain to grow to the longer chain hydrocarbons. So here we have the correlation, like ASF relation, which basically shows this is the mass fraction of the product with the n number of carbon atoms. So we usually draw it like in the form of logarithmic function to get the slope. That is basically chain growth probability. So here we have like a different catalyst in this paper, which they prepared like they tested cobalt catalyst, like cobalt prepared with the bicarbonate, carbonate based, and phosphated based, and COO, like with the different oxidation state, and finally the CO3O4. So this is the how like Faraday efficiency and partial current density varies with respect to different catalysts. So we can clearly see like cobalt is not a very active catalyst for the CO2 reduction, but when we try to polarize it in the form of bicarbonate, carbonates, and phosphated cobalt, and then finally going to CO3 or 4, then we can get like Faraday efficiency to some extent for the hydrocarbons. We can clearly observe from here C2, C3, C4, up to C6 and C7. However, this Faraday efficiency is very low, but in the coming slides, you will see like why this catalyst is very important, and this is very good finding actually. And here we can see the partial current density with respect to the different catalysts. So here you see like a chain growth probability. We can clearly see the carbon numbers and then this parameter. Uh, so for the cobalt catalyst, we can clearly see the chain growth probability of 0.54, which is very good actually. If we compare it to the conventional electrocatalyst, for which it is zero point 0.2 to zero point 0.3, so that is the point. That is a very good finding actually, because in this way we can approach like actual Fischer-Tropsch process in which like chain growth probability is up to zero point 0.9 or zero point 0.8. So this is like the key point of this paper. So now coming towards the catalytic evaluation. Uh, in the CO2 electroreduction, we try to combine the fields of CO and CO2, and then we check like how the catalyst is behaving. So this group actually previously published a phosphated nickel based catalyst, in which like reaction mechanism was a bit different, in which by adding CO with the CO2 field, the reaction basically goes through a different mechanism. But in this paper, actually, when they add CO along with CO2, we can clearly observe like the production rate is going to increase and it becomes like maximum anywhere in between zero point 0.5 to 0.66. And however, if we talk about like the ratio of alkenes to alkanes, it basically decreases when we increase this ratio. So this basically shows CO basically plays very important role in terms of production rate because it is going to add into the intermediates to get like long chain hydrocarbons. However, if we talk about the ratio of alkenes to alkanes, then alkenes are basically somewhat suppressed when we are going to increase the amount of carbon monoxide gas. On the other hand, if we are going to increase the potential, then we can clearly observe like production rate is going to increase, and that is quite obvious. And on the other hand, if we talk about like the ratio of alkenes to alkanes, it is almost constant throughout the potential range of zero point 0.7 to 1. So now coming towards the characterization of the catalyst. So here we can observe like in the X-ray absorption near edge spectroscopy, this is the reaction time, like this is in situ characterization. So with starting from 0 minute, which is a bit red, and going towards like 75 minutes, which is green. So we can observe like initially it is towards CO3 or 4, like we can observe here in this region, like here. And as time passes out, this gets reduced to some extent, moving towards this region that is CO foil, which means like during the reaction process, the oxidation state of cobalt changes basically from +4 to somewhat lower states, which means like some of the amount of the cobalt oxide is going to change to the cobalt metal. So that can be observed here as well. Like as time goes passes, initially the slope of changing the the cobalt oxide fraction is initially quite high because slope is quite high here. But then so it basically decreases with the passage of time. And it can also be observed from the HR10 because initially we are going to observe cobalt oxide, and then there appears FCC cobalt, and it is basically increasing with the passage of time, like after 1 hour and after 24 hours. And here in the in situ Raman, we can observe like there are some domains which are being reduced, and we don't observe any sort of cobalt oxide here after some reaction time. And there are some unreduced domains where we can observe like the presence of cobalt oxide even after 4 hours as well. So it means there are basically interface between cobalt metal and cobalt oxide, and there are some subsurface domains which remains somewhat intact, and the surface cobalt oxide is basically going to reduce to the cobalt metal, and that's why we can observe these sort of different domains like reduced domains and unreduced domains. So now coming towards the stability of the catalyst. So here we can observe like if we are going to increase the amount of cobalt oxide, then basically partial current density of the C2 plus products is going to increase linearly. We can observe it here. And if we talk about the Faraday efficiency with respect to time, so this is very interesting actually. Initially up to 100 minutes, the Faraday efficiency decreases when we apply the cathodic potential. And as soon as we apply a plus zero point 0.6 of the anodic potential, it basically gets recharged because it is going to get oxidized again. And we regenerate the domains that were initially reduced to the cobalt metal. And we can regenerate the catalyst, and we can get the same Faraday efficiency as we observed initially. And then it again starts decreasing with the application of cathodic potential. And again, if we try to apply like anodic potential, and then it again gets charged, and we can operate it in this way, like 100 minutes in the operation of actually CO2 reduction, and then for about some time, maybe 5, 10, 20 minutes, we can recharge it, and then we can apply again, go through the operation of CO2 reduction. So this is very interesting actually. So now we can observe like the energy dispersive spectroscopy here, like the presence of cobalt oxide, oxygen, and then both of these here. And here we can observe the same thing which we discussed here, like when we apply like cathodic potential, these peaks of cobalt oxide that disappear, and then we when we apply like anodic potential for like charging the catalyst again, here these peaks appear again, and here as well. And when we start to apply like cathodic potential, this starts to decrease, diminish the intensity of these peaks, which correspond to cobalt oxide. And here it actually almost disappeared completely. So this is actually very interesting. So for this, they performed like DFT study to get the insights, like what's going on the surface of the catalyst, how this is going to happen. So here we can observe like top view, side view of the catalyst, and this is the interface between the cobalt oxide and metallic cobalt. And here we can see, like we all know, like copper 100 is a very good facet, and copper is actually very good catalyst for the production of hydrocarbons, and it is like very active catalyst. So then they obtain like CO absorption energy on the surface of the different facets, like cobalt 001, and then here we have like a cobalt oxide, and here this is the plane for the copper 100, and we can observe like the interface of cobalt and cobalt oxide is very close to this copper 100 facet. So that's why this catalyst performed really well in terms of chain cross probability. And here we can observe like the initiation process of the reaction, adsorption of CO on any surface of the catalyst. And here we have like adsorption of CO on the surface of this interface, which is clearly a very moderate sort of binding energy, which basically gives us like growth, chain growth probability by enhancing the probability of the CC coupling. And here we can observe like CC coupling barrier for the different direction intermediates. And we can observe like this blue color of shows metallic cobalt, and this red color is like cobalt oxide. And we can clearly observe for the CO-CO coupling, the coupling barrier is almost same. And when we check it for like CO plus CH2, the coupling barrier is quite drastically reduced for the interface, and same goes with the other intermediates. And finally, the chain termination. I will talk about the chain termination. So basically, the binding energy of these intermediates is quite good. So that's why there is probability of like further addition of the intermediate, so that we can get like long chain hydrocarbons. So finally, what are the takeaway points from this paper? The first takeaway point is like we can obtain a very good chain growth probability even in the electrocatalyst, which is very good actually, and the highest ever reported the chain growth probability. And it is also very good in terms of stability because we can regenerate the catalyst for a little bit time by the application of anodic potential. And we can clearly observe like the interface of the metal and metallic oxide, which is playing a very important role in terms of chain growth probability. And the only like negative point of this paper is like Faraday efficiency is quite low in terms of different hydrocarbons because it is very, very low, maybe 0.45% for the all of the C2 plus products. However, this paper has very good other insights like chain growth probability, stability, and like importance of the interface. Okay, so that's all from my side. Thank you.
Thank you so much, Lukman, for a nice presentation. So I'm wondering for one little question like product efficiency. So is it
Yes.
0.45 or is 45%?
No, it is actually 0.45. Let me show you here. Okay, you can see here it is around maybe 0.48 or something 0.45. Threading efficiency is actually very, very low. But the main key point is like chain growth probability in this paper. And that's what they try to get the insights how they obtain like this much chain growth probability because we can observe usually it is between zero point 0.2 to zero point 0.3 for the electrocatalyst, but
Yes.
in terms of like thermal fission drop process, it can go maybe zero point 0.8, zero point 0.9. So that's the actual point of this paper.
No, I mean 0.45 is hydrocarbon. So what are the CO, methane,
Hydrogen.
hydrogen.
Yes,
So it means very less amount of hydrocarbon is forming there, and among them the chain growth probability is 0.54.
yes,
Mhm. Wow, interesting. Basically, I think their interesting point is mechanism,
yes.
like why they publish an advanced material. I think
Yes. You can say like mechanism, but they like have been through the different techniques and how they try to regenerate the interface between cobalt metal and cobalt metal oxide. So this is how like they published it in such a good journal.
nice. Actually, their regeneration point is also very good
Yes,
for, for
which
practical point of
very
view.
interesting actually.
Yes. Uh, and overall, professor is also very famous.
Yes.
Thank you. Thank you. If anyone other has any question, please.
Thank you so much, Lukman bhai. Can you please explain the recharge process? Just saw the figure. I didn't understand it, how they recharge the catalyst surface. It's like they just provide the cathodic potential.
Okay, actually, this is the cathodic region because like working catalyst is cobalt oxide. You can say like cobalt oxide and cobalt metal interface. So during the reaction process, basically cobalt oxide basically reduces to cobalt metal, and that's why it loses its activity to some extent, maybe about 120 minutes up to, and then they basically reverse the potential to the anodic potential, and then during this process catalyst basically gets oxidized again, like it gets itself regenerated to cobalt oxide, and there is interface is basically regenerated, between cobalt metal and cobalt metal oxide, and that's why the activity is basically regained again during this process, and then they again perform their reaction of CO2 reduction during this time, and this basically goes again and again.
There are three cycles that they recharge the catalyst or something like that. They didn't explain that how much cycle they recharge the catalyst surface and then.
Yes, actually, they didn't provide any sort of information like how up to how much cycles they did it, but in this paper they basically presented it up to 3 cycles, and their main the aim was like to show like we can regenerate the catalyst again and again. So I don't know, but for the some cases, like you can see in the HRTM, they did it for 24 hours as well. They like characterize it for 24 hours as well. So, but for the in terms of regeneration, they basically presented here like 3 cycles only.
This is very good point because I like it to recharge the catalyst and then again it will work. So I think this
Yes,
is the main key of this paper.
yes.
Thank you.
Mr. Ravi, yes, sir, Bilal sir, or Nafis bhai.
Uh, can you just I'm sorry I was late a bit.
It's okay. It's
Can you
okay.
show me just the title? Okay. Could you re-explain DFT part?
Okay. Okay, so in the figure A, we can observe like how they constructed the metallic cobalt and cobalt oxide interface with the different sort of arrangements like A-top, breached, and showing like how there is a hole between the atoms. This is basically side view. So here we can observe like the charge transfer, which basically helps in the CO binding on the surface of the catalyst. So this is the benchmark actually, copper 100. That is basically a very good catalyst in CO2 reduction. This is where the binding energy stands for the copper 100, and this is where like it lies for cobalt 001, and here it is for like cobalt oxide. So when they calculated the charge and the binding energy for the CO on the surface of the catalyst, they observed like the interface between cobalt and cobalt oxide is like very near to this region. That is basically benchmark. So which is basically the key finding and key point for the good absorption of CO on the surface of the interface rather than on only on the surface of the metal or on the surface of the oxide. And here for the figure C, we can observe like the initiation of the reaction because we are feeding the CO on the surface of the catalyst, and here we have the only the surface at the zero energy, and after the binding energy at the interface, binding energy is in the minus, which shows very good binding on the surface of the catalyst for the CO. And here we have like the CC coupling barrier because for the production of long chain hydrocarbons, we need to have like good CC coupling between the reaction intermediates. So here we have CO, and the coupling barrier is almost same for copper metal and copper oxide, cobalt oxide actually. And here we can observe the difference here, like between the metallic cobalt and the interface between the metallic cobalt and metallic cobalt oxide. So we can clearly observe the difference here. Like the coupling barrier is basically quite reduced in this case of the interface, so which is going to play a very important role in terms of the activity and in terms of production of long chain hydrocarbons. And this is finally the chain termination. Here we have like this intermediate, and we have the proton on the surface of the metal. And after basically this coupling of the addition of this proton with this intermediate, we can observe like for the interface, it is a bit on the bit higher end, and on the surface of like cobalt only, it is on a bit of lower side. So this is basically the final chain termination. So which is basically it basically helps in terms of chain growth. Like there's CC coupling going on the surface of the catalyst, and then it keeps on growing until it gets dissolved from the surface of the catalyst.
And what was the purpose of introducing copper? Copper 100.
This is basically the benchmark. Like they tested because copper is very good actually in terms of CO2 reduction. We can obtain like ethylene and propanol and these sort of products in a very good quantity on the surface of the copper. So that's why take they have taken it as a benchmark, and then they try to compare the binding energy of this benchmark with their catalyst.
So with the cobalt metal, it's more binding energy than cobalt oxide.
Sorry?
Am I okay? More binding energy is with cobalt 001 as
Yes,
compared to cobalt oxide.
yes. What happens actually, this CO binding is very strong on the surface of the cobalt metal. So it basically poisons the surface of the catalyst because of its strong binding. And here, the binding is almost uh, not possible because it is in positive. So what happens when we get like the interface binding energy is like very some sort of intermediate between strong and weak binding. So that's why this catalyst is performing really well.
That's the main thing. Yeah.
Yes.
So to utilize cobalt oxide for chain growth, if there is coupling of cobalt metal, then this work well in reference to
Yes.
copper. Yes.
Yes, actually, yes, because this is the like binding energy for the uh, CO on the surface of the copper, because there is no change in the oxidation state of the copper, so it remains like as a horizontal line. But in this case, like if we are going to increase the like interface between, like this is metallic cobalt, and when we are going to increase the interface between the cobalt and cobalt metal oxide till here, where there is 100% cobalt oxide. This is like in between, like intermediate sort of the interface between metallic cobalt and metallic cobalt oxide, which gives like better results in here, which is very close to
Yes.
this like copper 100.
Okay. As a student of CO2 hydrogenation. What you people think? How long uh, we would see a breakthrough in uh, uh, like uh, like we talk about the fuel? I think it's quite could be a stupid question, but how long? What you people feel? Another 25-year, 30-year, 40-year? Uh, if we are going to replace the fossil fuels with such kind of technologies, looking
Yes,
at the
actually,
temperature. Mm.
this is actually very hard to answer this question because there are some decades if we go to 2000 to 2010 and 2020, there was very boom of biofuels through pyrolysis and some other dehydroxidation, hydrodeoxygenation. So in the end, people got idea it is very complicated and very difficult to produce fuel through the biomass. So then they try to explore the other fields. So it is actually very hard to answer this question at the moment, but maybe we can observe this maybe in 20-25 years if it continues to do so, because initially we could only observe methane, and then with the research as research went on, we observed ethylene and ethanol on the surface of the copper as well. And recently there is a report published for the production of n-propanol in very significant amount. So we can say we can hope for so, but nobody knows what happens in future.
Okay, hope for the best. Do your best.
Thank you.